In April 1970, folk singer Joni Mitchell released a song called Woodstock about a festival she never actually attended. In the chorus, there's a line that has a strange relevance to today's topic. We are stardust. It sounds like a cliche, but from a scientific standpoint, she was completely correct. We really are stardust, made of atoms that were once floating freely in space, drifting inside the cloud of gas and dust that eventually collapsed to form our solar system. Every person, every planet, every living thing on Earth is built from material that was forged somewhere else, long before the sun even existed. So, what seeded that cloud with the elements needed for life? An explosion. Every galaxy in the universe, including our own, is shaped by a chaotic and violent mechanism that drives the evolution of its stars. A cosmic event that can build entire worlds and annihilate them in the same instant. That event is called a supernova. What is a supernova? The term supernova was coined in the 1930s, built from the word nova, Latin for new. A nova is a stellar event in which a new, luminous point of light appears in the sky, created by interactions between binary stars, before slowly fading away. A supernova follows a similar pattern of brightness, a sudden, brilliant peak followed by a long, gradual dimming over months or years. The difference is scale and cause. A supernova isn't a birth, it's a death. It's triggered by a catastrophic explosion that completely destroys the star responsible for it, rather than simply creating a new point of light. Supernovae happen in one of two situations. Either a massive star reaches the natural end of its energy-generating life cycle, or two stars in a binary system interact in a way that triggers an unstoppable thermonuclear reaction. Either way, the result is apocalyptic. An enormous burst of radiation is released, everything from radio waves to X-rays to lethal gamma rays, which tears through the star's surroundings and can devastate any planetary systems within roughly 50 light-years of the blast. The good news for us? Solitary, average-sized stars like our Sun are simply not massive enough to explode this way. Only stars with a mass at least 8 times greater than the Sun can generate the extreme gravitational and nuclear conditions required to trigger a true supernova. When a star that massive can no longer support its own weight, its outer layers collapse inward at tremendous speed, setting off an explosion billions of times brighter than the Sun, bright enough to outshine its entire host galaxy and to be seen from millions of light years away. In the process, material equal to at least 5 times the mass of our Sun is blasted outward with unimaginable force, creating a shockwave that travels for light years into interstellar space and typically leaves behind a glowing, colorful nebula. That expelled material floods the surrounding gas clouds with heavy elements forged deep inside the star's core, enriching the raw material available for the next generation of stars far beyond what the original star was born from. In other words, a supernova doesn't just destroy, it plants the seeds for what comes next. Historic supernova observations. Long before we understood what caused them, ancient civilizations were watching supernova light up the night sky. Throughout history, there have been several documented cases of supernova bright enough to see with the naked eye. Perhaps the most dramatic came in the year 1006 CE, when a supernova now catalogued as SN 1006 blazed in the sky for several weeks. At its peak, it was estimated to be more than 100 times brighter than Venus, bright enough to be visible during daylight and to cast shadows at night. It's considered the brightest supernova ever recorded in human history, and it triggered a mix of awe and anxiety among observers across the northern hemisphere. Japanese records describe it as white and blue in color, while Chinese astronomers referred to it simply as a guest star. By tracing historical accounts, modern astronomers pinpointed its likely location to the constellation Lupus, where a nebulous remnant roughly 1,000 years old can still be found today. About half a century later, another massive star exploded, this time in the constellation Taurus. It wasn't nearly as bright as SN 1006, reaching only about the brightness of Jupiter in the night sky. But it remained visible during the day and was recorded by Chinese, Korean, and possibly even Central American observers. The remnant of that explosion is one of the most heavily studied objects in our cosmic neighborhood, the Crab Nebula, a glowing cloud of stellar debris located around 6,000 light-years from Earth. SN 1987A, the last supernova we've seen with our own eyes. For a long time, astronomers assumed these bright, temporary lights in the sky were the birth of new stars, hence the name nova. It wasn't until the 1930s that scientists realized these events were actually the result of stellar explosions and coined the term supernova for the class of nova events in which the star itself is destroyed. Our understanding has only deepened since then, but there's a catch. Supernovae are genuinely rare on a human timescale. Statistically, we should expect one to occur within our own galaxy roughly every 50 to 100 years. Yet we haven't directly witnessed one happen inside the Milky Way since the invention of the telescope. We have, however, observed plenty of supernovae in other galaxies. The problem is that we can't predict where or when the next one will appear, and their extreme distances make it hard to measure their properties precisely. That changed dramatically in 1987. The Large Magellanic Cloud is a small, gas-rich dwarf galaxy located a mere 160,000 light-years from Earth, sitting in a relatively unobstructed patch of sky. Many of its hundreds of thousands of massive stars are far easier to observe than similar stars buried deep within our own galaxy. So when a supernova lit up this galaxy in the late 1980s, astronomers finally got their closest and clearest look at the phenomenon, gathering an enormous amount of new information about how these explosions actually behave.
What made it even more valuable is that scientists already had prior observational data on the star that exploded, a luminous blue supergiant. That meant, for the first time, theoretical models of supernovae could be tested directly against real, detailed observations. To this day, SN 1987A remains the last supernova visible to the naked eye from Earth.
Classifying supernovae. Finding and classifying supernovae used to be an extremely tedious process, relying almost entirely on amateur astronomers manually comparing photographs of the night sky, searching for any new points of light. Fortunately, automated computer systems and advanced sky survey technology have eliminated most of that manual labor. Astronomers can now scan millions of stars and billions of galaxies automatically. Even though we haven't observed a supernova inside the Milky Way since the early 1600s, we're now discovering hundreds of new supernovae in other galaxies every single year, some located deep in the observable universe. At first glance, these explosions can look fairly similar to one another, but by analyzing the light spectrum of an explosion as it happens, astronomers can determine which chemical elements are present. And that's the basis for how supernovae are classified, by the presence or absence of hydrogen.
Type 1 supernovae show no hydrogen in their spectrum. Type 2 supernovae do. From there, each category can be broken down further, based on the shape of the supernova's light curve over time, or the presence of specific heavy elements. This classification system was introduced in the 1940s by physicists Fritz Zwicky and Rudolf Minkowski. At the time, they had no supernovae inside our own galaxy to study, so the only examples available to them were extremely bright, distant, extragalactic supernovae. As a result, Type 1, technically the first category named, actually turned out to be the rarer, more luminous class, while Type 2 represents the more classic scenario, a massive star collapsing under its own gravity. We'll start with Type 2, since it's the more straightforward of the two, an explosion caused by a star reaching the natural end of its life, with hydrogen clearly present in its spectrum. Core collapse supernovae, Type 2. As mentioned earlier, only stars with a mass more than 8 times that of the Sun are heavy enough to end their lives in a supernova. Below that threshold, a star simply can't compress its core enough to trigger one. Some, like stars, fuse the hydrogen they're born with into helium,
and eventually fuse that helium into carbon. But that's usually as far as they get.
Far more massive stars, however, keep climbing the fusion ladder, progressively fusing heavier elements at ever higher temperatures. Each time one fuel source runs out, the core briefly contracts, making itself hotter and denser, and the process starts again. Carbon fuses into oxygen, neon, and magnesium. Once that's exhausted, the core contracts again and fuses those elements into silicon, sulfur, calcium, and argon. At an even more extreme level of compression, those elements finally fuse into iron. And this is where the star's energy-generating life comes to an end.
Up until this point, every fusion reaction inside the star released energy because each new element was more tightly bound than the last. Iron, however, is the most stable, tightly bound nucleus that exists. Fusing it further doesn't release energy, it requires energy. So the moment the star's core becomes dominated by iron, the fusion reactions that once held the star up simply stop producing power.
As iron builds up at the center, the energy output collapses, and the star can no longer support its own enormous outer layers. Those layers then fall inward under gravity's pull at speeds around 23% the speed of light. In a matter of seconds, a star dozens of times wider than the sun collapses into a ball of crushed subatomic matter roughly the size of a small city. But the particles inside that core don't collapse quietly. As the star's layers compress, free-floating electrons begin exerting an outward pressure that resists the collapse, though on its own it isn't nearly enough to stop it. Once the core's density exceeds several 100 billion times the density of water, negatively charged electrons are forced into atomic nuclei, merging with positively charged protons to form neutral neutrons. As more electrons get absorbed this way, there's less electron pressure left to resist the collapse, which only accelerates the process further. Eventually, the core becomes so dense, comparable to the density of an atomic nucleus itself, that neutrons begin spilling out of atoms entirely, almost like toothpaste being squeezed from a tube. And unlike electrons, free neutrons resist compression far more forcefully. That resistance abruptly halts the collapse once the core shrinks to somewhere between 12 and 25 kilometers wide. At that point, what remains is called a neutron star. If the original star was massive enough, that neutron star will keep collapsing further, eventually forming a black hole. But in either case, the sudden halt of the collapse, combined with the outward push from neutrons, sends a powerful shockwave rippling back through the star's collapsing layers. That shockwave alone, though, isn't quite enough to cause the scale of explosion we actually observe. There's a second, even stronger force at work: neutrinos. Neutrinos are strange subatomic particles that barely interact with matter or light at all. They're often nicknamed ghost particles for how easily they pass through nearly everything. They're produced in massive quantities every time a proton and an electron merge to form a neutron, and the sheer energy they carry is staggering. For a brief moment, greater than the combined output of every star in a billion galaxies. Even though neutrinos don't normally interact with matter, under these extreme conditions, a small fraction of their energy gets absorbed by the star's collapsed outer layers. That tiny fraction is still enough to unleash an explosion of unimaginable power, reversing the collapse and driving the star's material outward at incredible speed. The result is what we call a Type II, or core collapse supernova, an explosion that releases the energy of billions of suns within a matter of days, scattering the heavy elements forged deep in the star's core out into the universe. Elements essential for life, like oxygen, carbon, and iron. As the explosion expands outward, floods of newly created neutrons slam into atomic nuclei and get absorbed in a process called the R process, forging even heavier elements, including gold and silver, in the star's final moments. Subtypes of core collapse supernovae. Type 2 supernovae themselves are broken down into further subclasses based on how their brightness changes after the initial explosion. Stars between 8 and 15 times the mass of the Sun typically produce a Type 2p supernova, the P standing for plateau, referring to a period of slow, steady dimming before the light finally drops off. This is by far the most common subtype, accounting for more than half of all observed core collapse supernovae.
Somewhat rarer is the Type 2 linear supernova, produced by stars greater than 15 solar masses, which shows a steady, linear decline in brightness right after its peak. There's also the Type 2b, which shows only a single faint hydrogen line in its spectrum, the result of an aging star that had already lost most of its hydrogen shell before exploding. And the Type 2IN, narrow, which displays thin or moderately narrow hydrogen emission lines, believed to come from luminous blue variable stars, exploding inside dense clouds of material they'd already shed. Then there's Type 1, supernovae that show no hydrogen at all in their spectrum. This category splits into three subtypes: IA, IB, and IC. Types IB and IC are still fundamentally core collapse explosions. They simply lack any hydrogen signature. These are known as stripped core collapse supernovae, believed to come from extremely massive, unstable Wolf-Rayet stars, volatile stars with high metal content that generate powerful stellar winds, strong enough to blow away their lightest outer elements entirely. A Type IB supernova lacks hydrogen, but still shows helium, while a Type IC lacks both hydrogen and helium, representing an even more evolved and more stripped-down Wolf-Rayet star. Beyond the missing hydrogen, both subtypes behave much like a standard Type 2 explosion. That brings us to the most scientifically important subtype of all, Type IA. Type IA. And the discovery of dark energy. Unlike every type discussed so far, a Type A supernova isn't caused by core collapse at all. It happens in binary star systems containing at least one white dwarf. White dwarfs represent a different way for stars to end their lives. As mentioned earlier, stars under 8 solar masses aren't massive enough to climb the full fusion ladder. Their fusion process typically stops once carbon turns into oxygen. Without enough energy left to hold itself together, the star doesn't explode. Instead, its outer layers gently drift away, forming a glowing planetary nebula. What's left behind is the star's exposed core, an Earth-sized sphere of crystallized carbon and oxygen. That remnant is a white dwarf. On its own, a white dwarf is remarkably stable. When our own sun eventually becomes one, it's expected to remain faintly luminous for roughly a quadrillion years before finally going dark. But white dwarfs don't always exist in isolation. Many are part of old binary systems, paired with a companion star. That pairing sets up the conditions for a Type AA supernova. Every white dwarf carries a hidden, ticking limit. Once it crosses a specific mass threshold, known as the Chandrasekhar limit, an unstoppable runaway nuclear reaction ignites, and the star detonates, ejecting its superheated carbon and oxygen, along with silicon and iron, which show up clearly in its light spectrum. Under normal circumstances, white dwarfs never gain enough mass to reach that threshold on their own. But when a companion star nearby sheds material late in its life, some of that material inevitably falls onto the white dwarf, gradually pushing its mass upward. Once it crosses roughly 1.4 solar masses, the star detonates in what is, pound for pound, the brightest type of supernova there is, bright enough to briefly outshine its entire host galaxy from billions of light years away. Here's why that matters so much. Because Type 1a supernovae always explode at essentially the same critical mass. They always reach roughly the same peak brightness. That consistency makes them incredibly useful as cosmic distance markers, known as standard candles. If you know how bright something truly is, you can calculate how far away it is just by measuring how dim it appears and how much its light has shifted, or redshifted. Throughout the 1990s and early 2000s, multiple research teams used this technique to probe the depths of the universe and measure how fast it's expanding. At the time, scientists expected the universe's expansion to be gradually slowing down, held back by the combined gravity of all its galaxies. Instead, when astronomers began tracking distant Type 1a supernovae, they found the opposite. The most distant ones were dimmer, and therefore farther away, than a slowing universe could explain. It appeared as though the universe had expanded more in its recent history than earlier models predicted, meaning its expansion is actually accelerating. That single discovery, made using Type A supernovae, upended decades of cosmological theory and led directly to the concept of dark energy, a mysterious, repulsive force that appears to be pushing the universe apart at an ever-increasing rate. It remains one of the biggest Owen questions in all of physics today. Fritz Zwicky, the physicist who helped classify supernovae in the first place, originally proposed additional categories, types 3, 4, and 5, based on unusual individual explosions that didn't cleanly fit the standard classes. Today, these are largely thought to be imposter events that only mimic true supernova behavior. In modern astronomy, types 1 and 2 remain the primary classifications, grounded in decades of nuclear physics research and direct observation. Kilonovae, the other cosmic explosion. There's one more type of stellar explosion worth covering, one that isn't quite as bright or long-lasting as a standard supernova, but is still an apocalyptic and remarkably fruitful cosmic event in its own right. This one isn't caused by a single collapsing star, but by a pair of neutron stars, the dense, dead remnants left behind by earlier supernovae. If two neutron stars end up gravitationally bound to each other after their original stars explode, the result can be an even more extreme kind of explosion. As the two neutron stars orbit one another, their mutual gravity gradually causes that orbit to decay. The closer they spiral together, the faster they spin, eventually reaching speeds beyond 60% the speed of light, rippling the fabric of space itself and sending gravitational waves rippling out across the universe. Once the two neutron stars reach a critical distance, the tidal forces between them become so extreme that their otherwise indestructible outer shells shatter, exposing the ultra-dense matter inside. That matter, previously packed at roughly 500 billion times the density of water, suddenly goes from extreme compression to nearly zero pressure in the vacuum of space. The result is a brief but powerful explosion, not as bright as a supernova, but still detectable from billions of light years away, especially once paired with its gravitational wave signature. This class of explosion has its own name, a macronova, more commonly known as a kilonova. Kilonovae release enormous bursts of radiation, including their own type of gamma-ray burst, and like supernovae, they forge substantial quantities of heavy elements through the same R process. As neutrons flood through surrounding atomic nuclei and get absorbed, they produce elements like gold, silver, europium, and strontium. In fact, some scientists now argue that colliding neutron stars, not supernovae, may be the primary source of the universe's heaviest elements. It's not yet clear whether kilonovae happen often enough throughout the universe to account for all of it, but what is clear is this. Between supernovae and kilonovae, these two cataclysmic explosions are the only known processes in the universe capable of creating elements like gold and silver. So the next time you see a piece of gold or silver jewelry, remember what you're actually looking at. The product of a star that died in one of the most violent events the universe has ever produced. An explosion so powerful, it built the very atom sitting on your hand. We are, quite literally, made of the same material blasted outward from these cosmic catastrophes. Stardust, in the most scientifically accurate sense of the world. If you want to keep exploring the universe with us, hit subscribe. There's a lot more out there worth discovering.